All right, let's go ahead and get going with these. So we're going to talk more about domain today, and we'll probably talk about graphing some stuff. Maybe we'll get to inverse functions. But let's start with this. So finding domain, these are both square roots, and whenever we have a square root, we're always going to say that the inside stuff has to be greater than or equal to 0. For this first one, the first thing I would write down would be the inside stuff has to be greater than or equal to 0. This one's pretty easy to solve. You can just isolate x. I personally don't love multiplying or dividing by a negative across an inequality if I don't have to. So instead of like subtracting 12 and then multiplying both sides by -1, I would rather just add x to both sides, which I think is the easier thing to do. So I would say just 12 is bigger than or equal to x, or think of it as x less than or equal to 12. Which means my interval notation domain is going to be everything less than or equal to 12. So everything from -infinity all the way up to 12, inclusive of 12. Welcome, Lily, right? Yes. Also, I should mention, for those of you new or not new, you're always welcome to ask questions. So if I say something that needs clarification, or if I've written something that you can't quite see because something that I'm writing is not excellent, please, please, please don't hesitate to say, hey, James, I have a question about a thing. For the next one, it's a little more work. I'm going to start off the same way, though. I'm going to say that the inside stuff has to be greater than or equal to 0. I'm not a huge fan of adding 25 to both sides and then taking the square root. It's not impossible, but when you do it that way, in fact, let's talk about what happens if we do it that way. If I do it that way, I'm going to get x squared bigger than or equal to 25. And then if we take the square root of both sides, as you might have seen from class recently, the square root of x squared is not just x. The square root of x squared bigger than or equal to the square root of 25 means that the absolute value of x is bigger than or equal to 5, which really means x is bigger than 5, or x, I should say bigger than or equal to. We get x bigger than or equal to 5, or x less than or equal to -5. I would instead opt, if I could, to factor. So if I was doing this, I would say I've got x minus 5 times x plus 5 wanting to be bigger than or equal to 0. And then I would put that all in the number line. So on my number line, I'm going to get a 5 and a -5. Then I'm just going to start picking numbers. Pick something bigger than 5, like 7. 7 minus 5 is positive, 7 plus 5 is positive, and 2 positives multiplied together is positive. And then over here between -5 and 5, I pick 0. 0 minus 5 is negative, 0 plus 5 is positive, multiplied to a negative, and then over here it's going to be positive. And since I want the parts where it's positive, I want all of this where x is bigger than or equal to 5, and all of this where x is less than or equal to -5. That's the way I would personally prefer to get there. Both ways are right. I just feel like this way is a little easier to make mistakes doing it this way. Either way, we end up getting a domain that is everything from -infinity to -5 inclusive, union inclusive of 5 to infinity. There's our domain there. Now, really, the reason I asked these two questions is because I want to use them to find some domains of how we combine functions together. So there's kind of like, there's like 5 ways you can combine functions together. 4 of them are pretty normal: addition, subtraction, multiplication, and division. And then the 5th one, which is the one we actually use the most, is a composition of functions. So let's talk about what happens when we start adding or subtracting functions together, or multiplying or dividing. So let's say we're going to, oh, question, yeah.
Of 9 is just 3,
right.
And later on it's just like, oh, it could be.
Well, so we talked about this a little bit previously, but yeah, let's clarify that because it is an important clarification. In fact, so before we'll come back to this, I'm going to dedicate a whole page just to this topic because I think it's worth noting. So I'm actually going to go back to the thing I said before, which is the following. Yeah, let's start with this. The square root of x squared is equal to the absolute value of x, which I know is a weird thing to kind of say, but it's true. So a couple things I want to clarify. I'm going to use some examples, don't worry. First and foremost, I just want to point out the square root of x squared is not equal to just x. It'd be nice if it was, but it isn't. It's total, and here's why. If I take the square root of, what's my favorite number to pick here? Sure, let's do 8. Eight's my favorite number, by the way. I was born on August 8th. We'll talk, I think it's so 8 squared is 64. And what's the square root of 64? Right. It's not meant to be tricky. It's meant to be like, duh, of course it's 64. Okay, but now here's where things get a little bit more interesting. What's the square root of -8 squared? Well, what's -8 squared? 3. What's the square root of 64? 8. Positive 8. Not plus or minus 8. Not -8, but really just 8. And so I just want to point out to all of you that this is doing the same thing that an absolute value function would do. If I said, what's the absolute value of 8? You all would tell me 8. If I said, what's the absolute value of -8? You all would tell me 8. These two functions do the same thing for every value of x. That means they're the same function, even if we call them different things. And that's actually generally true. One second. If two functions do the same thing for every possible value of x, they are the same function. Yeah, Kyra.
So, like, for the -8 squared, you know how, like, if we square root the exponent, why doesn't it just cancel out?
Well, that's a really good question, actually. Yeah, I like your question. I don't know if I have a good answer to it, actually. Because you would certainly say, like, just off to the side here, if I was writing 8 squared to the 1/2, usually when you have a power to a power, yeah, how am I going to justify this here? Good question. That'd be 8 to the 1, which is 8. -8 squared to the 1/2. Yeah. So I think there's something about the domain here, and the problem is that usually these things are interchangeable. Usually when you have a power to a power, it doesn't really matter which way you write the power, the order of the powers, meaning, like, I could say 2 to the 3rd to the 4th is the same as 2 to the 4th to the 3rd is the same as 2 to the 12th. Right, because that's 2 to the 3rd times 2 to the 3rd, right? It's a lot of 2's multiplied, 12's multiplied. But when you're talking about interchanging these powers, we're making some assumptions, and the assumptions are kind of whatever you're raising to the power is in the domain no matter what. And the problem is, this is not true here. -8 to the 1/2 squared. You can't take the square root of -8 because it's not in the domain of the square root function. So you ask, I think your question is really excellent and very subtle. I don't know if my answer is really, really great, but I'll tell you that the reason that it's not working this way is because we can't take a square root and get a negative number out. And the real kind of reason, so here's kind of the big picture reason why all of this is working the way it is. It's because once upon a time, a bunch of people decided that we want the square root to be a function. So we have all decided that we want f of x equal to the square root of x to be a function. And to be a function, you have to meet some very specific criteria. I mean, generally a function is just a rule, right? Rule that says, give me an input, I give you an output. But I'm gonna be a little bit more precise with my wording here. You give me an input, and I give you exactly one output. So if I said the input's 9, what's the square root of 9? Right, not plus or minus 3, because I can't give you 2 different y values for the one x value you're giving me. That's why we don't want a plus or minus, which is why we have to say that we've all decided the square root of 9 is equal to 3, not the square root of 9 is equal to plus or minus 3. It's kind of annoying, but it is true. Now, let me just give you one more minute before I know there's a question, but let me just say one more thing. This is different than solving. If we're going to solve the equation x squared equal to 9, well, I think we can all agree that before we even do any work, 3 is certainly a solution, and -3 is also a solution. Now, why are we getting the solutions? Well, it's because of this up here. If I was going to solve this, here's the shortcut end of the situation. The end answer is x equals plus or minus the square root of 9. That's usually what you do, right? Whether you're solving x squared equal to 9 Or if you were solving x squared equal to something less nice, like 7, you would say that my solution was x equal to plus or minus the square root of 7. One of those simplifies more, right? Square root of 9 is obviously 3. So this is going to be x equal to plus or minus 3. But here you just have to leave this as plus or minus root 7. There is no making that answer any nicer than it already is. Square root of 7 is an irrational number, can't be written as a fraction, doesn't have a repeating decimal, doesn't have a terminating decimal. But the work that we didn't show, that's kind of always built up into that quick little process you probably have done for many years at this. Wow, maybe not. Maybe you haven't done this before. But certainly, if you've done this before, you're like, yeah, you just throw on a plus or minus. But the reason why is because here's what we're actually doing. If I take x squared equal to 9, and I take the square root of both sides, well, the square root of x squared is equal to the square root of 9. And the square root of x squared is the same as the absolute value of x. What we're really saying here is that the absolute value of x is equal to the square root of 9, which is 3. Only 3. But then if the absolute value of x is equal to 3, that means x could be positive 3 or negative 3. All right, I will pause for a moment and open the floor to questions. Not that the floor is always open to questions, but sometimes I ask you to hold on because I want to say something. Any questions?
So do we really use the like plus or minus when we're solving inequality?
Yes, an equality or sometimes even an inequality, but the inequality is a little bit like when we started off was a little bit more work, but yes. Yeah, that's fairly true. I mean, yeah, I would say so, yes. So just to kind of go along with this theme for 1 second. So when you think about when I think about the square root function, so when I graph f of x equal to the square root of x, I'm getting just the nice, like I like to usually plot some points like if x is 0, the square root of 0 is 0. If x is 1, the square root of 1 is 1. If x is 4, the square root of 4 is 2. Those are my usual points I like to graph. So I'm going to get the point 0, 0, and 1, 1, and 4, 2, and 9, 3. I'm just going to kind of eyeball it. There's your square root function. F of x equal to the square root of x. Let me contrast that with the other thing I'm going to say, which is that, on the other hand, if I say that this is y equal to the square root of x, and then I square both sides, I get y squared equal to x. Now, these aren't quite the same. Or are they? Are they the same? Did I do the right thing? Right, x equal to y squared, yeah. So here's the difference. In this equation, y can only ever be positive. Whereas in this equation, y can be positive or negative. So the difference between this and this is the graph of y squared equal to x, or maybe I would think of it as x equal to y squared, looks like this. It's like a rightward opening parabola. And as far as we're all concerned, this is not a function. It fails the vertical line test. So that's kind of the most of the story. This is not a function. Most of the story as to why this whole square root thing works the way it does is because we want it to be a function. We want our graph to pass the vertical line test, which means when you input an x value, you can only get out one y value. Whereas here, if I put in, let's say x equal to 4, I could get y equal to 2 or negative 2. And that's what's making it kind of fail the vertical line test, is you're getting 2 outputs for 1 input. Okay. So, long story short, whenever you take a square root of something, you just get the positive value. Whereas if you're solving a quadratic equation, where x squared equals something, or x squared plus 5x plus 6 equals 0, right? That's a quadratic equation as well. You typically get 2 different solutions because you're getting a positive or a negative of your radical with some other stuff. Yeah.
So on the test, back to the quiz, it's like, it says to, if it doesn't say to solve or evaluate, just pick one solution.
Yeah. Yeah, I would say so. Now we'll get there in a second. Actually, we'll come back. We'll come back around. Yes. Okay. So let's look back at those functions we started with and talk about how to combine functions. So combining functions, it's not really that exciting combining functions, except for maybe the composition. So if we look at, say, the same functions, f of x equal to the square root of 12 minus x, and g of x equal to, what did I have here? The square root of x squared minus 5, sorry, minus 25, apologies. Then the way you can add, subtract, multiply, or divide functions is exactly the way you would think it would work. Meaning if I say, what's f plus g of x? It's literally just f of x plus g of x. Which in this case is going to equal the square root of 12 minus x plus the square root of x squared minus 25. And you can't, at least in this example, combine these in any meaningful way. They're kind of just stuck, separated like that. You can't put them together in one square root. Oh, before I forget, when you have a chance, you have to do it. Do fill out the attendance form by scanning one of the laminated QR codes. There's one there. Not the higher up ones, or the ones that are taped to the wall, the ones that here. So when you have a chance, fill the attendance form, please. So, not very exciting. But what's interesting about an addition of two functions is that the domain is going to be potentially different than either of the original functions we start with. So what's the domain of f plus g of x? Well, the way I think about this is essentially where the domains overlap. So we have to meet both conditions, right? For the first function f of x, right? We need, I'm just going to write them up over here real quick. For f of x, we needed x to be less than or equal to 12. For g of x, we needed x to be less than or equal to -5, or x to be bigger than or equal to +5. So if you pick, say, like x equal to, let's say x equal to 8, x equal to 8 is totally fine here, and totally fine here. If you pick something like x equal to 4, x equal to 4 definitely works there. 12 minus 4 is a positive number. I can always take the square root of a positive number. But 4 is not going to work here, because 4 squared is 16, and 16 minus 25 is -9, and I can't take the square root of -9 and get a real result. So what we need is the overlaps, or the intersection of these two domains. I think it's easiest just to draw a picture. So I'm going to draw my number line. I'm going to label all the important points, which are 12, 5, and -5. And I'm just going to kind of draw each of the domains in a different color. I do have purple. Yeah, we'll see if how this works. Okay, so cool. So for f of x, I'm going to draw the domain in red, and it's going to be everything less than or equal to 12. So here's 12, and then here's everything less than or equal to it. Great. There's the domain of f of x. And then for the domain of g of x, it's going to be everything bigger than or equal to 5. And everything less than or equal, I should say, or everything less than or equal to -5. So there's the domain of g of x. And what we need for our domain is wherever they overlap. So they certainly overlap everywhere left of -5. Ooh, yeah, purple works. So all of this, you can't really see it that well though. So there's where they overlap in purple. And they also overlap between 5 and 12. So everything from here to here. So what we can say is that the domain of f plus g of x is going to be x less than or equal to -5, or x between +5 and +12. Or in the interval notation, -infinity to -5 with a bracket, union +5 to +12 with a bracket. Question, Shereen.
Why won't
X less than and equal to -5 instead of greater than and equals to.
So when we solved x squared minus 25 greater than or equal to 0. So this is where you can do it one of two ways. Sorry, papers. So. Yeah. So when you're solving, right, when you're saying that the insides have to be greater than or equal to 0, I did this, and I personally prefer to factor. I like to go over here and factor, and then say, well, if I pick a number over here, the whole thing's positive. And if I pick a number over here, the whole thing's positive. Like if I plug in -6, -6 minus 5 is negative, -6 plus 5 is negative, and the negative times the negative is a positive. But you can also do it this way, where you bring the 25 over to this side and take the square root of both sides. But then you have an absolute value inequality. For the absolute value of x to be bigger than or equal to 5, either x has to be bigger than 5, or smaller, or I should say more negative than -5. Right? If you plug in -7, the absolute value of -7 is bigger than or equal to 5. So that's why we're getting those two sections. Typically, with an absolute value inequality, you either get everything to the sides or everything in the middle, one or the other. So, yeah, papers. Oh, okay.
How do we do like overlapping to find domain versus like plugging in numbers and testing?
So, good question. What I would say is the overlapping specifically is when you're talking about either adding, or as we'll see in a second, or subtracting or multiplying or dividing two functions. So it kind of required us to already have found the domains of f and g, and then to subsequently see where they overlap. Here, whereas the plugging in kind of part is what you do when you're just starting out. You're like, well, I've got something I need to work. I know it's not. Well, I'm going to clarify that a little bit more to go on. What I want to say here, the good news about this is, once you found the domain of f plus g, with one small caveat, any other combination that's not a composition, meaning f minus g or f times g or f divided by g with a little extra work, is the same. So here's what I mean by this. If I look at f minus g of x, which is just going to be f of x minus g of x, which is just the square root of 12 minus x minus the square root of x squared minus 25. I still have all the same domain problems that I had in the previous problem. X still needs to be less than or equal to 12, and x still needs to be bigger than or equal to 5 or smaller than or equal to -5. This has the same domain as f plus g of x. And it still is -infinity to -5 with a bracket union bracket 5 to 12. And wonderfully, so is f times g. F times g, which I don't love, right? So if you write f times g the way I write it, make sure you make your dot small and not like a circle like the composition symbol looks like. So f times g of x is just f of x times g of x, which is just going to be the square root of 12 minus x times the square root of x squared minus 25. I will mention here, you could actually multiply the insides together and multiply it out and simplify. I don't know if I would call that simplified, but you could certainly make this look simpler, I guess. I probably wouldn't. The domain is still the same. If I look at this, and I should really stress here is that when you're finding the domain of some combination of functions, you should definitely look for the domain before you do any simplifying. Because whatever you've got there, you have to obey the rules of what you've got there, no matter how you change that. So looking there, I still have to do the same thing. X still needs to be less than or equal to 12 and still has to be bigger than or equal to 5 or less than or equal to -5. So I'm still going to say domain is once again everything from -infinity to -5. I probably don't even need to write it again, but I'm going to. The last non-composition combination, division, does have one extra thing we have to look out for, which is something we always have to look out for when you have division. We don't want to divide by 0. So if I look at the domain of f divided by g of x, which is just going to be just like every other addition, subtraction, multiplication, or division, just works out to be exactly what you hope it would be. It's going to be f of x divided by g of x, which in this case is going to be the square root of 12 minus x divided by square root of x squared minus 20. Could you combine this together? Of course you could. Yeah, but I don't really want to. But yes, you could totally write this as the square root of 12 minus x over x squared. Interesting. Yeah. And what I would point out here is we still have to obey the same things, but we still need, I'm going to say for the 5th time, x to be less than or equal to 12 and x to be less than or equal to -5 or bigger than or equal to +5. Additionally, we don't want the denominator to be equal to 0. So we know that our domain is kind of the same in that it's going to be most of all of this, negative infinity to -5, union positive 5 to 12. But we need to make sure we're going to exclude wherever the denominator is equal to 0. Which means we're going to exclude 5 and -5 because those values of x make the denominator equal to 0. So we want to exclude x equal to plus or minus 5. So our new domain here for f divided by g, the domain would actually be negative infinity to -5 exclusive union exclusive of 5 to 12 inclusive.
Yes, but I got the same answer, but instead of putting equal to 0, I put greater than 0.
That's also fine. Yeah. Well, it's okay. I think what you probably did, and just to clarify, you probably said that the insides are greater than 0. That's totally fine because we already know for the square root, the insides have to be greater than or equal to 0. But if my denominator hadn't had a square root in it, then I would have not cared if it was positive or negative. Yeah, that's totally good. And then just to kind of go all the way full circle, if I instead did the domain of g divided by f, in fact, you all should write it. Find the domain of g of x divided by f of x, which is going to be the square root of x squared minus 25 divided by the square root of 12 minus x. It should be very similar to the ones we just did. I'll give you a moment. So what's the only difference between the old domain and the new domain? What number do we have to exclude? 12 is the culprit. So our new domain here is going to be domain of f divided by g of x is going to be negative infinity. I should say it is not equals negative infinity to -5 inclusive union inclusive of 5 to 12 exclusive. That's good. So for the other three combinations, f plus g, f minus g, and f times g, all of them have essentially, I feel like I'm just making sure in my head. I don't think they're ever different. I think f minus g, f plus g, and f times g always have the same domain as each other. F divided by g or g divided by f is a little bit different. You have to make sure you look out for where the denominator might also be 0. Great. Okay, so it's interesting as these four things are, they're not as important as a composition. So what you really want to look at is what's going on with F composed with G. And there's a couple different ways of writing this notation. So composition of functions, which is certainly easier to write out as F circle G of X, but in my opinion, better way of doing this every time is just to write F of G. They're equally, they mean the same thing. I wouldn't say they're equally good. I like the second one much better than I like the first one. And the reason I like the second one is because I feel like it's more informative. I feel like it's really kind of telling me what to do. So let's look at those two functions. We're still dealing with the same functions. Let's look at for F of X still equal to the square root of 12 minus X, and G of X still equal to the square root of X squared minus 25. Let's look at what F of G of X is. My words of wisdom when it comes to composition of functions is work from the inside out. Meaning, if I'm going to think about what F of G of X is, I like to replace G of X with the function that it's equal to. So I would write this as F of the square root of X squared minus 25. And then I know that F of X is 12 minus X. But what I'm really saying when I say that in my head is F of a thing is equal to the square root of 12 minus the same thing. Or what I really like to do is write, instead of F of X, I just like to write F of parentheses is the square root of 12 minus parentheses. Whatever's in the parentheses goes in the parentheses. And then I don't really need those parentheses because I have a square root there, but it's good to write them. So F of G of X is equal to the square root of 12 minus the square root of X squared minus 25. Domain is a little dicier when it comes to composing functions. I feel like it's almost a compost there. Yeah, all right. Sure.
Okay, the second one is.
When you say the second one, which one are you referring to? F or G?
That's my question.
Okay, so I wouldn't refer to either of them as first or second. The words I would encourage you all to use instead of first or second, or there was another thing like first or last, I don't know, is the inner and the outer function. G is the inner function, is the one that is being input into F, which is the outer function. Those are the words I would use. So G of X is definitely the inner function. F of X is definitely the outer function, at least in this example. We could also look at G of X, which we will in a second. Yeah. We'll talk about the domain for a second, but I feel like we should use some examples, or we just kind of do some examples. So when I'm thinking about composing functions, I'm thinking about domain, there's a good rule of thumb, it's always true, and that's the following. For the domain of F of G of X, we always must obey the domain of the inner function. Because the inner function is going to show up. At least normally it will. That's an interesting question. Huh. Yeah, even if it doesn't actually, yeah, you could ask some dumb questions. Sorry, I just thought something that was kind of stupid. But maybe I'll say stupid things later if it makes sense to. So in this example here, whatever else happens, we know for sure that X has to be greater than or equal to 5. Or X has to be less than or equal to -5. That for sure has to occur, because if that's not the case, then the square root of X squared minus 25 will be giving me imaginary numbers. Right? If X is 4 here, that's a problem. It's not going to work. After we have written down that we're obeying the domain of the inner function, then we also have to look at the whole composition and see, are there any other things that might be problematic? So after this, we then have to look at, well, I've got the square root of some stuff. And I know that if I have the square root of some stuff, that stuff has to be greater than or equal to 0. So we're also going to say that the total insides here, 12 minus the square root of x squared minus 25, has to be greater than or equal to 0. I would add the square root of x squared minus 25 to the right-hand side. I'm going to say that 12 is bigger than or equal to the square root of x squared minus 25. And then I'm going to square both sides. So, fun fact, if something is bigger than something else and both things are positive, which they are, 12 is positive, square root always gives us positive results, as we've talked about extensively today. It's totally fine to square both sides and you'll still retain the direction of inequality. If A is bigger than B, A squared is definitely bigger than B squared. So we can definitely say that 12 squared is bigger than or equal to x squared minus 25. And I'm going to add 25 to both sides. 12 squared is 144 plus 25 gives us 169. So 169 is bigger than or equal to x squared. And now you have a choice, just like before. You can either square root both sides, or you could bring everything to one side and back. I guess I'll square root both sides. If we square root both sides, you're going to get square root of 169 bigger than or equal to the square root of x squared. What's the square root of 169? 13. 13 is bigger than or equal to, okay, everybody, now you know the answer. I'll give you a second. What is the square root of x squared? Yeah, absolute value of x. Okay, so the absolute value of x is less than or equal to 13. That means x could be as big as 13 or as negative as negative 13. But it can't be any more negative than negative 13. It can't be any more positive than positive 13. So we're stuck with x being between positive 13 and negative 13. Totally. So the other option here, just to write it up here, is if you brought everything to one side, I would certainly pick the side where x squared is positive. So I would rewrite this as x squared minus 169 is less than or equal to 0. Bringing everything, I'd like to write things on the left-hand side, or you could write it as 0 is bigger than or equal to x squared minus 169. It's the same thing. And then if you factor this, the difference of squares, it factors as x minus 13 times x plus 13, less than or equal to 0. Then I do the number line. On my number line, I'm going to get a positive 13 and a negative 13. You pick something bigger than 13, like 15. 15 minus 13 is positive, 15 plus 13 is positive, and positive is positive is positive. And then you can either keep doing that, or you can use the trick we talked about a class or two ago, where we observed that since each of these factors has an odd power, the sign's going to change every time. When you pick something between negative 13 and 13, you're going to get a negative times a positive, which is negative. And if you pick something less than negative 13, you're going to get a negative, which is positive. But unlike most of the other times, we actually want the negative parts here, right? We wanted x squared minus 169 to be less than 0. So we want everything between negative 13 and 13. And that's why we're getting everything. Okay, so now, yeah. You can do either way. Yeah, so you can either plug in the values for each potential section of your number line, or you can say, well, 13 came from this factor, that factor had an odd power, so the sign's going to change. Nick. Yeah, we can't really do that for the overlapping part. So now we need to meet both of these conditions. We need for x to be bigger than equal to 5 or less than equal to negative 5, and between 13 and negative 13. So we're kind of stuck between we want to be bigger than or equal to 5, but less than or equal to 13. So between here and here, we don't want to be between negative 5 and 5 because that doesn't satisfy that. And then we want to be less than or equal to negative 5, but no further negative than negative 13. So our domain here is going to be bracket negative 13 to negative 5. union bracket 5. 13. Still obeying the domain of the inner function, but then also having our domain reduced by whatever's happening with our overall composition. Let me look at one thing here. The other composition is not nearly as interesting. Well, let's write it down just to kind of make sure that we see. It's really worth knowing that when you compose two functions, the order of composition definitely matters. Almost all the time, with one notable exception, you get wildly different things if you compose things in different directions. So if I go the other direction and say, what's g of f of x? Well, again, I'm going to work from the inside out. F of x was the square root of 12 minus x. I'm going to get g of square root of 12 minus x. And then g was the function, the square root of x squared minus 25. So I'm going to get the square root of, instead of x squared, it's going to be parentheses squared. And then I'm just going to fill in the parentheses. Okay, so once again, notably here, I need to obey the domain of the inner function. So the domain of the inner is x less than or equal to 12. Or if you prefer, negative infinity up to 12. And then we should simplify this if we want to find the overall domain. So simplifying, the square root of 12 minus x squared is just 12 minus x. So it's worth pointing out, and I should have said this maybe earlier, but I'll point it out now. It's worth pointing out that the square root of x squared is the absolute value of x. And the domain is everything, right? You can plug in positives or negatives and you always get a result. On the other hand, if you take the square root of x squared, well, first let me ask you all. I'm taking the square root of x as the inner function and then squaring it later. Is my domain limited? Can x be negative here? Definitely not. We can't take the square root of a negative number and then square it later. It's not going to work out. So here, our domain is, well, x can only be greater than or equal to 0, or if you prefer, 0 bracket to infinity. And then the square root of x squared, you don't need the absolute value, even if it would make sense, because since x is already positive, saying it's equal to x, you're only going to get positive things anyway. X is already, I should say non-negative. So when you square a square root, you get just what's inside. When you take the square root of something squared, you get the inside part's absolute value. So what I was trying to say in the longest way possible is that g of f of x is going to equal square root of square root of 12 minus x squared is just 12 minus x. And then we still have minus 25. And then I would simplify that just a little bit. 12 minus 25 is negative 13. So it's negative 13 minus 6. So I want to find the domain here. I'm just going to set the insides to be non-negative or greater than or equal to 0. So negative 13 minus x has to be greater than or equal to 0. Fine, I'll do it the way I don't like. So usually I would just add x to the right, but I'll do it the other way just to point out, to make sure everyone remembers that we have to do a thing, we do a thing. So if I add 13 to both sides, I've got negative x bigger than or equal to positive 13. And then if I multiply both sides by negative 1, I'm going to get x less than or equal to negative 13. Multiply by negative, you have to change the order of the inequality. Which seems not unreasonable, right? If I pick a number less than I always like to check. Like if I pick a number like negative 15 and I plug that in, does that work? Yeah. Negative 13 minus negative 15 is negative equal to positive 2. And we can totally take the square root of 2. I mean, it's not a nice thing. It's an irrational number, but it is a real number that exists. So that checks out. So now I'm going to see where they overlap. Let's see, I've got positive 12, I've got negative 13, and here's positive 12, everything less than or equal to 12. And now here's negative 13, everything less than or equal to negative 13. And it looks like they overlap just here. So everything to the left, that's all the overlapping. So it looks like the domain of my composition for this one is the domain of G of f of x is just going to be everything from negative infinity up to negative infinity. So here I will point out, you could have gotten away with not looking at the domain of the inner function and everything would have worked out just fine. But that's not always a safe bet. So you always should, if you're looking at the domain of a composition of functions, look at the inner thing first and then see what else happens. Okay. So there were some other questions here. Yeah, let's look at that one. Cool. Yeah, we should talk about, sure, let's go that way first. So I typically, it's nice that you're all in the same class. It means there's only one kind of thing that's going on, no one's in different places. So I've been looking at your homework assignment. There's a couple interesting problems. I thought this one was, I feel like these two problems are kind of, that's what I'm looking for. I don't know, not very specific. So let's say we're given something like, I'm just going to make something up here. Given, sure, h of x equal to the seventh root of x over x squared minus 3. We want to write this as a composition of functions. F of g of x. And I'm always, when I'm looking at this, I'm always thinking about g of x being the inner thing. So if I look at the seventh root of stuff, a bunch of stuff, I'm already saying it in my head. Oh, I've got the seventh root of, oh, the thing that's the seventh root of, the of part is probably the inner function. That is probably the g of x. So not that this is the only option, but the option that is most likely the right choice or the natural choice. You say, well, it looks like g of x is probably going to be just the inside stuff. The g of x is typically the inside stuff. This is going to work less well for the other example I have, but it's still going to work. Now, it can be kind of hard to identify f because I want to write f of, well, in fact, I could say f of g of x should be f of what I've just said g of x was, which is x over x squared minus 3. But then what's the result I want to actually get? Well, I want to get the function that we started with, meaning I want to get the seventh root of x over x squared minus 3. So let me ask all of you. I want you to think about this. What did I do to the things inside the parentheses here? Something relatively simple, right? It's not like a complicated. All I did was I took this and I took the, right, that's it. So I could say more generally, if f of g of x is just equal to the seventh root of g of x, the way I really want to write this is f of x is the seventh root of x. That's the more normal way to express the outer function. If you're writing this in web work, you could try to write it like this, but it's easier to write it as f of x equal to x to the 1/7 power. That's usually into web work than trying to find a seventh root button somewhere. There was some, oh yeah. Let's look at this other example. Yeah, sure. Yeah, fine. I'm going to change that up. I'm going to make it different. How different? Not that different. Do I have enough room? Yeah. Let's say we have some other composition like g. I should fine. G of x equal to. Sure, let's do that. Let's say it's 2 tangent of x over 6 plus tangent cubed x. This one I feel like is a little harder. It's a little harder to identify the inner function here. Yeah.
Yeah, I don't have a good way of thinking through the thought process of how I'm identifying what I'm identifying.
I can actually, there's one thing I would do. When you have trig functions raised to powers, this is the shorthand notation for it, but you might, and especially when we start taking derivatives of trig functions to powers, it is usually in your interest to write this as 2 times tangent of x over 6 plus, instead of writing it as tangent cubed x, writing it as tangent of x cubed. To me, that tangent of x being cubed is a good indicator that maybe tangent is a good choice for the inner function. It's not the only choice, but it's probably the easiest. So if I was going to try and write this as some f of g of x, and I know I chose capital G over here. They're not related at all. I just happen to, it's a common choice. I would probably choose the inner function g of x to be tangent of x. And then essentially to find f, what I'm going to do is I'm going to take all the instances of what I've chosen for g and replace them with x, so that I can see that f of x then has to be 2 times x over 6 plus x cubed. So that when I put in tangent for each x, I get exactly back the composition I was trying to kind of rebuild. I will point out, it is not a very natural process to find functions that make a composition, like it composed to another function. That's not something that I think is a fairly typical thing we do in calculus. Is it a useful skill? Maybe. When we start talking about the chain rule, it's good to be able to see how functions are compositions, but actually being able to do this, I don't think is that important. Like it's not useful, but it's just yeah. Let me have you all try one. So let me make something up, not too heinous. Sure. Let's say we have j of x is equal to, sure, yeah. Let's say it's the natural log of x squared minus 3 over x squared minus 3 to the 4th plus 1. I want you all to try and write this as some f of g of x. Try to think about a good choice for what your inner function might be while I go fill up my water bottle. So I think that the inner function I think I tried to make it not, I feel like I was trying to make it not too obvious. Maybe I made it too obvious. I don't know. It's never too obvious in math. I think g of x equal to x squared minus 3 is an excellent choice. And then if I replace each of those, I'm essentially saying j of x equals the natural log of g of x over g of x to the 4th plus 1. You can even make this a composition of 3 functions if you really wanted to. We don't. So then that's going to be my f of g of x. So then my f is just natural log of x over x to the 4th plus 1. Kind of weird. What happens when you make up stuff right off the top of your head? Sometimes things come out kind of weird. There was something else. Yeah, okay. We'll do one more domain thing, and then we will try to move on and talk about graphing some stuff, some exponential function stuff. So Let's just use a new piece of paper. Let's say, oh, and I had an example here that I made up. I don't love that example though. It's a little gnarly, but fine, we'll look at it anyway. Let's say, for example, we had f of x equal to the fourth root of x plus 1 and g of x equal to the, let's say third root of 16 minus x. It should not be too terrible, I think. Maybe, I don't know. All right. So we want to talk about what the domain is of their compositions, kind of any composition. But first of all, so if I'm ever asked about domain of f of g or d of f or f of f or g of g or whatever, I kind of need to know what the domain of the original functions are to start off with. So even though I'm not being asked, I'm still going to point out that for this function here, I need the insides to be greater than or equal to 0. Or in other words, I need x to be greater than or equal to negative. Here, there are no restrictions. Cube roots, odd roots, no problems. No restrictions. In case this isn't clear, I want it to be clear. So let me just say two things here, maybe more than two things. But here's what I would point out. The square root of 9, yes, we know is 3. The square root of negative 9, boo. Not real. I should point out, because it's going to come up eventually. 17C, we are going to talk about imaginary numbers, and they're going to be super duper important when we talk about the behavior of some systems of linear differential equations. That said, for now, we're not worrying about it. When it takes square root of negative, it just doesn't matter. But eventually it's going to matter. So don't, I just don't want you to get stuck in your head that like, we're never going to do that, because eventually we are going to talk about imaginary numbers in a couple of quarters. On the other hand, or what I really want to say is, why is the square root of 9 3? Shereen, I don't want you to answer this one because we talked about this earlier. Someone else tell me, why is the square root of 9 3? Why is the square root of 9 3? Yeah. Has to be positive, but why not? Why not 4? Like, why isn't the square? Yeah. It was Shayla. Yes, Shayla. Exactly. That's why the square root of 9 is 3, because 3 times 3 equals 9. In the same sort of way, the cube root of 8 is 2, because 2 times 2 times 2 equals 9. Equals what? Equals 8. But the cube root of negative 8 also works. The cube root of negative 8 is negative 2, because negative 2 times negative 2 times negative 2 is negative 8. Which I know you can't read because that looks terrible. So the thing I'm trying to point out here is just that you can always take the cube root of a negative number or a positive number. Cube roots, fifth roots, seventh roots, any odd root, you can always take the odd root of any positive or any negative number. They don't always come out nice, just like square roots don't always come out nice, right? The cube root of negative 7, I don't know exactly what it is, but I know it's an actual real number that exists. There is some number that if you multiply it by itself 3 times, you get back negative 7. It's probably like negative 1.9 something. In fact, you can plug it into a calculator and figure out what it is. I don't have one. Actually, I do. It's not true. I do. Cube root of negative 7, just in case you're curious. I want to know now. Negative 7. So the one I can show you all two. Can you see that? Not really very well. No. Let me just tell you. Negative 7 to the 1/3 power, or the cube root of negative 7, is about negative 1.91. So if you do negative 1.91 to negative 1.91 to negative 1.91, you get pretty close to negative. So when it comes to domain, odd roots, no problems. Even roots, usual problems. Can't be even root of a negative. So if we compose, say, yeah, we'll do them all, or we're going to run out of time. We're always going to do f of g of x. That's going to be f of the cube root of 16 minus x. So far, no problems, right? The inner function has no domain restrictions. So I move on with my life. And I write this as the fourth root of my stuff, the cube root of 16 minus x plus 1. And now this is where things get kind of gross. They made up a problem that's kind of gross. So now what we're going to see is, okay, the insides have to be non-negative. The cube root of 16 minus x plus 1 has to be greater than or equal to 0. Fortunately, this is not too terrible to solve. I'm going to subtract 1 from both sides and say the cube root of 16 minus x is greater than or equal to -1. And I am going to cube both sides. I'm going to raise both sides to the third power. I get 16 minus x is bigger than or equal to -1. I'm going to add x to both sides and add 1 to both sides so that 17 is bigger than or equal to x. Or in other words, x is less than or equal to 17. Or in other words, my domain is everything from -infinity to 17 inclusive. I always like to do a quick check. If I plug in something just a little outside the domain, I should get some problem. So if I were to plug in, say, like, I don't know, 18, 16 minus 18 is -2. The cube root of -2 is more negative than -1. And something more negative than -1 plus 1 is going to be negative. That's a problem. Can't take the fourth root of negative. So anything that's outside of this domain seems like it's a problem. That's good. I want that to be true. So I could have picked an easier number. Like I could have tried to make it work out. Like I could have picked x equal to 24, which is also outside of the domain. And then 60 minus 24 is -8. And the cube root of -8 is -2. And -2 plus 1 is -1. That's a problem. So you don't have to check that, but I like to do a check to make sure I'm thinking about the right thing. The one I really wanted to address, though, was I really don't want to. I feel like I should do them all, but let's look at g of x first of all. G of x. So I've got g of the cube root 16 minus x. No problems. Cube root of 16 minus x can be anything. And then I'm going to have, well, g of that is just the cube root of 16 minus parentheses, which is, of course, cube root of 16 minus x. And even though this looks super funky, there's nothing that indicates I have any domain restriction. Are there any divisions by 0? Oh, definitely no fractions at all. There's no way I could be divided by 0. Are there any logarithms? Definitely not. Are there any even roots? For sure, no. Kind of wild. So here, since there aren't any of the 3 things that make us have domain problems, domain's everything. You don't have to do any work at all to see the domain's everything. Yeah. Right. Well, I would clarify. We have to look at the domain of the inner function, and then after that, we have to then look at the composition and see if there's anything extra.
Oh, okay. So even if it was just the square root of 16 minus.
But the square root would be a different problem. See, the square root is problematic and the cube root is not. So what I would point out is in the first problem here, when we did the inner function had no issues. So then we moved on and said, oh, but now our composition, there could be some issues. So we have to set the insides to be greater than or equal to 0. And we did. We encountered an issue that x had to be less than anything bigger than that is going to be a problem. So if x is bigger than 17, 16 minus x is going to be 2 negative. So then when we take the cube root, we get something really negative, and then really negative number plus 1 is still going to be negative, and then the fourth root of the negative. I'm a little terrified to do the other 2 compositions because I just made this problem up before class to make these 2 problems work, but I didn't check those. So let's just look, but maybe not actually finish. If we look at g of f of x, g of f of x is going to be g of, oh, where's f of x? It's the fourth root of x plus 1. This is going to be g of the fourth root of x plus 1. So already we know that from the inside function, that's telling us x plus 1 had better be greater than or equal to 0, or x had better be greater than or equal to -1. For sure, has to be true. There might be more restrictions after that. For sure, that's a restriction. Okay, but then g of whatever is just the cube root of 16 minus whatever is in the parentheses, which is the 4th root of x plus 1. Which I would drop those parentheses and write it like this. Good news. Doing all this didn't add in any restrictions. As long as x is bigger than or equal to -1, the 4th root of this will be something that's real. And then 16 minus a real number, take the cube root of that, no problem, right? It doesn't matter what happens here as long as this works out. So this is our domain. There is no other restriction. And now for the one I'm really worried about, f of f. Let's look at f of f. So f of x. It's probably going to turn out to be terrible. Sometimes math is terrible. So it's going to be f of the 4th root of x plus 1. Cool. So that means just like before, the insides have to be positive. So x is bigger than or equal to -1. And then if we do f of that, it's going to be the 4th root of parentheses plus 1, where what's in the parentheses is the 4th root of x plus 1. And I think I might have lucked out. I don't think I have any problems. And here's why. Well, in fact, let me write this more nicely. So the 4th root of x plus 1 plus 1. As long as x is already bigger than or equal to -1, it has to be, then the 4th root of x plus 1 is going to be positive or negative. Like, I know it's kind of a terrible question, but what's the 4th root of 81? What's the square root of 81? What's the square root of 9? And the 4th root is a square root twice. So the 4th root of 81 is really the square root of the square root of 81, which is the square root of 3. And it's not -3, right? Just like the square root of something is always positive, the 4th root of something is always positive. So this is always positive. And if you take an okay, fine. I need to be more specific with my language. Non-negative, right? We have to include, it could be 0. So this is always non-negative. I could have just said or 0, I guess, but you know. If you take something that's greater than or equal to 0 and you add 1, it's always positive. And so the insides here are always positive no matter what I pick for x. So there's no additional thing I have to worry about. So my domain is the same here as it was before. Still -1, 2, 3. It might not always work out that way though. In fact, if this had been the 4th root of x minus 1 and then it was a -1 there, then there would have been more work to do. But we're not going to worry about that. Didn't have that. Great. Yeah, cool. Time is it? 2:50. Time flies by. So let's talk about some graphical stuff for a minute. Yeah, I'm curious where you're going to get to tomorrow in class, but we'll see. So let's talk about exponential functions. Exponential functions. Like y equal to 2 to the x. Let's use some colors. Yeah, colors. Or y equal to 3 to the x, or even y equal to e to the x. We're going to graph all these, but there's something I want to say first is that when I'm graphing an exponential function, I'm thinking about the general shape. In fact, yeah. So you want to have a good idea of what exponential functions look like, but I want to show you what they look like just for a second. If I just start graphing things all not perfectly. Let's pull up Desmos for just a second. I do think you need to have a good intuition without over relying on this, but Desmos is a great tool. So if we graph y equal to 2 to the x, your usual exponential shape, increasing from left to right, has a horizontal asymptote as you go out to the left of y equals 0, has a y-intercept of 1. And that's true for any exponential function whose base is larger than 1. I could throw a y equal to 3 to the x at you. Oops, not 3 to the 3, James, 3 to the x. And it looks very similar. In fact, let's zoom in just a little bit because, right? Similar, but it gets steeper faster in either direction, actually. Or you could even do everyone's favorite, y equal to e to the x, which they kind of look very much like they're on top of each other because they kind of are. E is pretty close to 3. E to the x is pretty close to the 3 to the x graph. One more thing. What is E? It's kind of like pi. It's an irrational number. It has a non-repeating infinite decimal. But what I would really say for now is E is about 2.7. That's what you should really know for now. E is about 2.7. It's close to 2.7. It's between 2 and 3. It's a little closer to 3. And then let me just show one more. If our base were to be between 0 and 1, like say 1/2 to the x. Oops, don't do that. Oh, sorry, blowing it. There we go. It changes the way it looks. It's still the same shape, but now it's decreasing from left to right instead of increasing from left to right. That's because as x gets larger, 1/2 times 1/2 times 1/2 more times gets smaller and smaller and smaller and smaller and smaller. One more thing I wanted to say here. Oh, it's escaping me. Still has a horizontal last note, y equals 0. There really was something else that I wanted to mention though. I totally forgot. Fine, I guess. Okay, so gosh, I really wanted to come back to it because I felt like it was something good. Oh, I know what it was. One more thing. Our bases should be positive. There's also a couple numbers that don't work very well either. Like your base could be 1, but it's not real exciting. 1 to the x is not really an exponential function because 1 to any power is just 1. 1 to the x is a constant. 0 is also not exciting. 0 to any power is 0 or undefined if the power is negative. But what I really want to point out is negative bases are not a thing we want. And here's why. If you do something like -4 to the x, oops, to the x, come on. You can't even really see anything. Yeah, you really can't. You can try to graph stuff, but it's going to be really kind of gnarly. You're not giving me anything, really? I'm kind of surprised. Sometimes they'll give you like dots to show you some of the points where this exists, but this function is not defined for most values of x. Because like, for example, if x were the 1/2 power, -4 to the 1/2 is the square root of -4, which isn't a real number. So bases shouldn't be negative either. And I was hoping Desmos was going to give me more there, but it didn't. Can I not like close you at all? Am I stuck with you forever? No, I can do that. Cool. So here's what I would say about graphing exponential functions very, very briefly today. We'll say more about this on Thursday. Is that when you graph an exponential function and your base is greater than 1, it's going to have the usual shape. The usual shape being looking like this. There's y equal to the x. And it's going to go through the point 0, 1, and it's going to have a horizontal asymptote of y equal to 0. And the only real difference between 2 to the x or 3 to the x or e to the x or any base to the x is how steeply it does this. So the higher the base, the faster it's going to go up and up and up. And that's when the drawing skills kind of start to evade me. If I was going to draw like y equal to 3 to the x, it would look something like that. And then since e is between 2 and 3, the graph of e to the x is literally squished between the graphs of 3 to the x and 2 to the x. It looks kind of like this. But very generally, I would say when you're graphing an exponential function, it has this usual shape. And you even have it already on you, maybe depending on how lined or not lined your right hand. You look at your right hand, that line there kind of looks like e to the x. And the reason I really say this is because later on when we talk about the natural log function, my hand is not great because I am old and have lots of lines on my hand, but there's kind of a line there that looks like the natural log as well.
make sure you look at your right hand, and many of you are right-handed and, you know, don't look at your right hand, right? The left hand is other functions. And then, yeah, just the last thing to say here is if your base is something smaller than 1, so if your base is larger than 1, then y equal to b to the x is increasing, which just means it's getting larger as we go from left to right, higher and higher and higher. On the other hand, if your base is between 0 and 1, that's the right way, James, then the exponential function y equal to b to the x is decreasing. For example, I'm always bad at drawing it the opposite way for whatever reason. Yeah. Something like y equal to 1/2 to the x. The last thing I'll say about this is that y equal to 1/2 to the x actually is literally the reflection of y equal to 2 to the x in the y-axis. There's a couple ways to see this, but one way is to actually plot. One way is to write it as 1/2 is 2 to the -1, and then you have 2 to the -1 to the x, and you have a power to a power, and you multiply those powers together. So this is really y equal to 2 to the -x. And when you put a negative on x, it totally changes all of the x values from what they were to their opposite values. So, yeah, I got it. Yeah, I know I said the last thing, and this is still the last thing. It's just a continuation of the last thing. So I just want to point out if I pick some x values like 0, 1, 2, and 3, 2 to the 0 is 1, 2 to the 1 is 2, 2 to the second is 4, 2 to the third is 8. 2 to the -0 is still 2 to the 0, which is 1, but 2 to the -1 is 1/2, 2 to the -2 is 1/4, 2 to the -3 is 1/8. And if I pick other x values like the negative numbers, like -1, -2, and -3, we get the exact opposite thing happening. 2 to the -1 is 1/2, 2 to the -2 is 1/4, 2 to the -3 is 1/8. And here, when you plug in a negative, you get a negative. So 2 to the -1 is just 2 to the 1. 2 to the -2 is just 2 squared. 2 to the -3 is just 2 to the third. So the idea is that you've got these, when x is positive, these values are big and these values are small, but then when you flip them, you get the reverse. So here, if I plot these points at 0, 1, and 1, 2, and 2, 4, and 3, 8, and then -1, 1/2, and so on. Here's y equal to 2 to the x. And then if I plot the other ones, where x is -1, -2, and -3, well, then I get -1, 2, -2, 4, and -3, 8. And so they are very literally reflections of each other. And so I just want you to see that when you put a negative sign on the x, it reflects the function across the y-axis. Okay, I stopped talking because it's 3:01.